So I would like to give this presentation on polymer-derived ceramics. They're functional, that we use this material to functionalize carbon nanotubes. And in this presentation, I will give some let's say, recent gas sensing results. So when we look at the carbon nanotubes, obviously they have lots of advantages. So they are sensitive, they are conductive, and then you can really make small structures with them. But of course, they have also disadvantages. The first one, that we need to find a way to produce an easy method. We need to find a really good method to produce them easily. And second, we need to control their properties. But this is valid in every material that we are preparing metal oxides, and we have the same problem with the metal oxides because it's difficult to control their sensing properties. And then reproducibility. That is also valid in metal oxide or carbon nanotubes. We have low reproducibility. And we need to improve the selectivity or sensibility of the material. So in this work, we used carbon nanotubes because they have high surface area, and we coat them with a semiconductor ceramic, and we can use also catalyst above the ceramic. Obviously, polymer-derived ceramics, it's quite new subject, although it has been published 100 years ago, the first time. So what we have is, at room temperature, we have a resin, we have a liquid phase precursor. It can be siloxane or it can be a silane. And then we are taking it, we are giving the shape, whatever shape we want. And then we are cross-linking it, we are heating it till 300 or 400 degrees. And then, if we want, we can also increase the temperature to make it amorphous ceramic. It has been already published about this polymer-derived ceramics. Actually, it was proposed as a MEMS device, as a thermal actuator, and we can also shape, as you can see, very small devices can be done with a good accuracy. When we look at polymer-derived ceramics, how conductive they are, actually it changes with the composition. Here you can see the ternary diagram. There's oxygen, nitrogen, silicon carbide. So when we increase the oxygen, of course the conductivity is quite low, but it's the same as the nitrogen. So if you increase the nitrogen, also the conductivity is quite low. But we found that there is an optimum range why, let's say, oxygen to nitrogen ratio 1:1 is a higher conductivity. So if you can use this range, you can get high conductivity, like 0.1 ohm centimeter per centimeter. So how we prepared the samples? It is we used an easy method. We used a carbon fiber substrate that in the market you can find easily, and then we deposit it with electrophotoretic deposition, as you can see. So we use the carbon fiber as electrode, and we mainly dip coated the ceracet, which is a polysiloxane, in a diluted form, and pyrolyze it at 1100 degrees. So how it works is that we have a substrate that is carbon fiber. Then we are growing carbon nanotubes on it. And then we are coating it with semiconductor ceramic. So obviously it has a clear advantage of creep because you are coating with a ceramic, so it can stand mechanically. It is giving it strength. And then the interesting thing is it is limited to a monolayer, so you don't need to do an extra thing. Itself, it is limited to a monolayer. And no, even if you increase the weight percent, even if you want to coat more and more, the conductivity, it doesn't decrease a lot, which is showing us that the ceramic itself is conducting. And the decrease in the conductivity, let's say 20%, when you put 50% of polymer-derived ceramic on carbon nanotubes, it's just because you are increasing the contact resistance. Another really interesting thing is because you're coating with a ceramic, now you can coat also another layer of catalyst and increase the conductivity or selectivity, which is a quite big issue in carbon nanotubes. So with the with the polymer-derived ceramics on top of carbon nanotubes, you can reach the surface. You can reach the monolayer of catalyst on top of our carbon nanotube polymer-derived ceramics. So as you can see, this is a sketch how it works. We have the carbon fiber substrate, we have carbon nanotubes, we have a ceramic layer, let's say monolayer, and then we have also a monolayer of precious material, catalyst basically. So it is a kind of sandwich structure. Here you can see clearly that we are growing carbon nanotubes on the carbon substrate. And also you can see that we have very good distribution of silicon. Here it is the silicon distribution you can see from this TM image. And when we come to the gas sensing properties, we know that carbon nanotubes are like p-type. They usually behave like p-type. So we have the reducing agents like ammonia or hydrogen or carbon monoxide, or oxidizing agents like nitrogen dioxide. Here you can see with the temperature, the behavior is exactly like a carbon nanotube. We don't change its property. It's still p-type response. With the temperature, we didn't change it that much, so the ammonia response doesn't change. So we have a little bit of increase in the sensitivity, but still, even at room temperature, you can still see the sensitivity at room temperature. Of course, higher the the higher the concentration, gas concentration, higher the response. We have response time. It's 15 minutes to 8 minutes, with the increase 15 minutes, of course, at room temperature, and 8 minutes at higher temperatures. Still, the recovery is quite high. It's more than 1.5 hours. When we look at nitrogen dioxide, we can see that it is it's more evident that when you increase the temperature, the sensibility is increasing. So the sensitivity is increasing gradually here. And here the response time, of course, decreases a lot from 24 minutes to 2.5 minutes in 200 degrees at 5 ppm. But as you can, so this is higher the concentration, higher the response, and the recovery time is still really high. The good thing about so we have really still we couldn't find a solution about the recovery time, of course. But the good thing about this material is ceramic coating is giving the good reproducibility. So even if you prepare two samples from the same batch, you are getting almost similar gas sensing responses. So this is for ammonia and this is for nitrogen dioxide. And so we think that this is quite important as a starting. I was early as well. So here are the conclusions. So first of all, of course, we know that we have lots of things to do. It's a new approach, so we need to start from something. So we believe that these polymer-derived ceramics coated with on top of carbon nanotubes, it's quite promising. And ammonia sensitivity is quite stable. It doesn't change a lot from room temperature to higher temperature, which is quite good. Nitrogen dioxide sensitivity, it increases with the temperature. So here we don't have that much selectivity. Let's say it is detecting nitrogen dioxide and ammonia at the same time. But the good thing is all the results that I showed you, they were without the catalyst. So we believe that if you put the catalyst on it, you can get the selectivity and you can increase the sensibility. Thank you.